Welcome to the part 3 of the transistor lecture series. In previous lectures, we have seen the overview of transistor, what are the different types of transistors. Then in part 2, we have discussed the working principle of PNP transistors. And here we would like to explore the working principle of NPN transistors. So just recap our previous knowledge, the symbol for transistors. So this is the symbol for PNP transistor and this is the symbol for NPN transistors. Now let us have a look here. This is the working principle of NPN transistor. Let us try to understand with these diagrams, figure 1 and figure 2. So figure 1 is showing this no external bias is provided to the NPN transistors, and just like our concept of diode or PN junction, barrier potential develops, and in N side we have the majority charge carriers as the electrons, and P side we have the majority charge carriers as the holes. So these electrons will diffuse here. So in the barrier potential we have negative potential towards P side and positive towards N side. Similarly here also we'll be having the same kind of things. So we'll be having this kind of barrier potential now under no bias condition. Now let us consider a situation where we shall be providing forward bias. So you see here, this is inside, emitter is our inside, and we are providing forward bias to this. That means negative of the battery is connected to the inside and our base is of positive material, so we are providing the positive bias here. So it is this base emitter junction. Earlier we have seen that we have named it as JE, and collector base junction we have given a symbol JC. So base emitter junction is forward bias and collector base junction is reverse bias. So here positive terminal of battery is connected to the N side, so that is providing us the reverse bias. Now here what we have, the majority charge carrier as the electrons are the majority charge carriers. Okay, here we have some holes, and once again here we have the electrons. Now as soon as we are applying the forward bias, these electrons, here we have the heavy concentration of the electrons, so these electrons will start moving. So consider this is our bowler, this emitter is the bowler. Okay, so now this is a test match, and in a test match base is a batsman. So base is batsman, and like in test match what happens, majority of the balls are left alone. So here majority of the balls will reach over here. So collector is our, it is collecting the balls, that is our wicket keeper. Collector is our wicket keeper. So emitter is the bowler, base is the batsman who is connecting very less number of balls or playing very less number of shots as it is a test match. And here as a result of that we shall be having less number of recombination, and majority of the electrons will be passing through the base, and the reason is what, it is very thin as well as very lightly doped. So most of the electrons are passing from the emitter to collector, and collector is collecting. That is very good. Now the flow of electricity is opposite to the flow of current. So that is a basic concept all of us must know. The flow of electricity is opposite of flow of electrons. Flow of electrons. Okay, so small corrections here. So the direction of the flow of electron and flow of electricity or flow of current is opposite to each other. So that means when electrons are flowing from emitter to collector, the current is flowing, IC is flowing in this direction. So this is exactly the opposite direction that of the PNP transistor. So here also we'll be having the opposite direction, that is IB is towards base and emitter current is flowing like this. So that is the major difference between NPN and PNP transistors. Now there are similarities. So if we now see the symbol and this circuit diagram, so we find that once again IC and IB are combining to provide IE. So we can write IE is equal to IC plus IB. So this is just as that of the PNP transistor. It is similar to the PNP transistor. So from here we can further write that the collector current is IE minus IB, and once again this is the reverse bias, so we have a dark current. So here we have ICBO. Why ICBO? We are considering this CB stands for the connected to base dark current or the reverse saturation current, because this is the reverse bias, and also we can say that this is the common base configuration. So next lecture we will be discussing what is the transistor configuration and what are the different types of transistor configuration. That will be detailing in the next lecture. But here for the time being, what we are seeing that this particular junction, collector base junction, is reverse biased, and here we have a dark current or the reverse saturation current, which is given the name as ICBO. So as a result of that, IC is slightly higher than that of this. So we can write IC as current gain alpha DC into IE plus ICBO. So if you see these equations are not changing, though the direction of the currents are changing for the two different cases, PNP and NPN transistor, but their relation is not changing. And if we have IC is much greater than ICBO, then we can say that alpha DC is IC by almost equivalent to IC by IE. So this is what we call the common base current gain. So this is important parameter alpha DC, and alpha DC we shall further elaborate in the discussion of a common base configuration, how transistor exactly works and what are the characteristics for input output relation for transistor in the common base mode, that we shall be taking on the next lecture. So here we end the discussion on the working principle of NPN transistor. Thank you very much.